You arrive at a property after a storm. A large red oak is leaning slightly toward a driveway. There's a cavity at the base, the crown is heavier on one side. The homeowner asks, "Is it going to fall?" Under ANSI A300 Part 9 tree risk assessment, risk is defined as the combination of the likelihood of failure, the likelihood of impact, and the consequences of failure. In simple terms, we are asking three questions. How likely is the tree or a part of it to fail? If it fails, how likely is it to hit something? And if it does hit something, how severe would the damage be? Today, we are focusing on likelihood of failure, and that comes down to biomechanics and mechanics. Mechanics is the study of how force affects objects. Biomechanics is simply mechanics applied to living things. When we assess a tree, we are asking a basic question. Is the load acting on this tree greater than its load-bearing capacity? Load means any force applied to the tree. Gravity is always acting on the tree. That is called static load. It does not change unless the mass changes. Wind is different. Wind is dynamic. It changes in speed and direction. It comes in gusts. That changing force is dynamic load. When wind pushes on a crown, it creates drag. Drag is the resistance caused by air moving across leaves and branches. The denser the crown, the more drag. You can think of it like holding a sheet of plywood in the wind versus holding a rake. The plywood catches more wind. That is drag. That wind force acting on the crown creates what we call a bending moment at the base of the tree. A bending moment is simply a force multiplied by a distance. That distance is called the lever arm. Think of a breaker bar loosening a lug nut. The longer the bar, the easier it is to turn the nut. The length of that bar is the lever arm. In a tree, the lever arm is the distance from where the wind force is applied in the crown down to the base of the stem or the root plate. The taller the tree, or the higher the center of gravity, the longer the lever arm. That increases bending moment. The center of gravity is the point where the mass of the tree is balanced. If a crown is heavier on one side, that center shifts. The center of pressure is where the wind force is effectively pushing. If those 2 points do not line up, the tree can experience torsion. Torsion is twisting. You have seen this when a tall, one-sided pine twists during a storm. Now let us talk about what happens inside the stem. When a tree bends, the wood on one side is being stretched. That is tension. The wood on the opposite side is being squeezed. That is compression. Between those two zones is a line called the neutral plane. At that line, the wood is not being stretched or squeezed. Here's the key point. The outer fibers of the stem carry the highest stress. Stress simply means internal force per area. If you snap a stick over your knee, the break starts on the outside edge, not in the center. That is because bending stress is highest at the outer fibers. This is why decay location matters more than decay presence. If decay is in the center, near the neutral plane, the tree may still have significant load-bearing capacity. If decay removes the outer tension wood, especially on the side under tension during bending, the strength drops dramatically. This is where taper becomes important. Taper means the trunk is wider at the base than higher up. A larger diameter increases resistance to bending. You can test this yourself. Try bending a thin dowel versus a thick one. The thicker one resists bending more. That increased resistance is related to something called section modulus, which is just a measure of how well a shape resists bending moment. Trees naturally build taper to handle increasing bending moment toward the base. Trees also reconfigure in response to load. If a tree leans, it forms reaction wood. In hardwoods, tension wood forms on the upper side of the lean to pull the tree upright. In conifers, compression wood forms on the lower side to push it upright. That is biomechanics in action. The tree is adjusting its structure to handle force. Live crown ratio also plays a role. Live crown ratio is the percentage of the tree height that has living branches. A higher live crown ratio usually means better energy production and often better structural adaptation. A tree with a very short live crown may not have the energy reserves to reconfigure effectively. Now let us talk about dynamic movement. When wind hits a tree, the tree sways. That sway has a frequency, meaning how fast it oscillates back and forth. Every tree has a natural frequency. If wind gusts match that frequency, movement can amplify increasing stress. Damping is the tree's ability to reduce that movement over time. Mass damping occurs when branches and foliage absorb and dissipate energy during sway. Think of shock absorbers on a truck. They reduce bouncing. In a tree, branch architecture helps reduce excessive oscillation. Defects influence how stress is distributed. Cracks are stress raisers. A stress raiser is any feature that concentrates stress in one area. If you notch a piece of lumber and bend it, it will break at the notch. Included bark at a branch union acts the same way. It reduces proper wood-to-wood attachment and increases the chance of shear failure. Shear is a sliding type of failure. If you have ever cut a branch and watched it split downward along the grain, that is shear. Torsion or twisting can split a stem vertically. This is common in trees with asymmetric crowns during high wind. At the root level, friction between roots and soil provides anchorage. When soil becomes saturated, friction decreases, anchorage weakens, that increases the likelihood of root plate rotation under bending moment. Everything comes back to a simple principle. Failure occurs when stress exceeds strength. Load produces stress, the tree's structure determines strength, decay reduces strength, geometry influences stress distribution, and crown structure influences load. Under ANSI A300 Part 9, your job is to evaluate whether the expected load, static or dynamic, is likely to exceed the tree's load-bearing capacity, given its biology and structure. When you understand bending moment as force times lever arm, when you understand that outer fibers carry the highest tension and compression, when you recognize stress razors and reduce taper, you are not guessing, you are applying mechanics. Tree risk assessment is applied biology and applied physics combined, and when you integrate those principles into your evaluation of likelihood of failure, you make defensible, professional decisions grounded in how trees actually respond to force. Thanks for listening to the Arborist-podcast. Let's keep building your arborist knowledge one domain at a time. If you found this useful, please like and subscribe.